All right. Well, hey, today, welcome to Differential Equations. 1 month ago here, we're in the home stretch for sure. Um, Today's plan, we're going to keep talking about the series solutions, but specifically, we're going to start talking about singular points, right? Because we've been able to avoid them for the most part by doing some changing the centers of our series solutions. But sometimes, depending on the form, sometimes when we've got singular points, we can still find solutions without using power series. Excuse me. And we're going to want to do that, right? If possible, we want to avoid power series. So I'm going to show you a class of equations called Euler Equations, which is probably the most famous of them that we can get around using power series. So good deal, right? But before I do that, I want to open it up to you guys. Any questions on any of the homework or anything we talked about so far you'd like to talk about?
Yeah, I have a quick question. If we're working with the spring mass system and we're
Mhm.
given things in imperial units,
Yep,
if I wanted to, find the mass, like the actual mass of an object, do I divide it by gravity
you
every
do.
time?
Yep. So
Okay.
you take the weight, which would be your pounds, and then you have to divide it by gravitational acceleration in our system,
Yeah, it's like
which is
32.2.
32 feet per second squared. Yeah, it's 32 something, but you can just use 32. Um, but yeah, so you basically find it the same way you find mass given force in metric, in newtons. You just divide by the 32 instead of the 9.8. Yep.
And does
So
that go with pound force as well?
what do you mean? So pounds are force. Pounds are the unit of force in the imperial system. So did you mean maybe foot pounds?
I don't know. I was reading last night about there's pound force and then pound weight or pound mass is what it said, and it just confused me, but I'll disregard that.
Yeah, I'm not sure what that is. I know that, well, that's one of the issues that we have just with our system is that when we talk about pounds, right, you stand on the scale and you weigh 240 pounds. Like that's not actually a mass, even though we kind of think that way. It actually is a force. It's the gravitational force. And so, um, yeah, anytime you see pounds, think of them as forces because regardless of what the book says, because never trust a math book when they're talking about physics, just like you should never trust a physics book when they're talking about math, right? Because stuff gets lost in translation. We do things slightly differently depending on which world we're in. Um, so regardless of what the book says, go with pounds as force because pounds are force. All right, and Ralph, I saw you threw in the chat box there 6-1 number 15. I'll go ahead and we'll look at that as well. And then Jesus gave me 6-2 number 6. Cool, got it on the list.
I think I know why they're asking about those questions because it's the same reason why I asked my question.
All right, stupid imperial units.
Honestly, no, everyone keeps saying metric is better, and like, yeah, it's easy to use, but I never really understood it until this homework.
Why you want metric?
Yes,
Yeah,
for sure.
there's no question that metric is far superior, just in terms of functionality, usefulness, right? Like memorization, you don't have to memorize anything other than the prefixes, right? Like I think I told you guys that when I was at the gym, someone was like, "Kilometer, how long is that?" And I was just like, 1,000 meters, just like off the cuff. And she gave me the nastiest stare. I was like, "What? That's what a kilometer is. It's 1,000 meters." So, but yeah, just like metric is far superior. So I'm guessing these two are both using our stupid system.
Yep.
All right. Well, let's go see what we can do about those. Let's see. And I'm sorry I don't have everything kind of ready, because normally when my computer's not being all funky, I'm better at it. All right, so let's look at number 15. So a 6-pound weight stretches a spring 6 inches in equilibrium. I think that wording is a little bit weird, but okay, so basically that's going to help us find our K, right? So suppose an external force of 3/16 sine omega t plus 3/8 cosine omega t pounds is applied to the weight. For what value of omega will the displacement be unbounded? All right, so basically that's what's going to lead to resonance. What's going to lead to what we saw with that video of the Tacoma Narrows Bridge. What's going to make it mathematically that as we look at that graph and it moves, it just like grows up. I mean, it's going to oscillate, but the amplitude of the oscillation continues. All right, so that's what that's asking. So let me go ahead and write down the pertinent information here. And then we'll go to the whiteboard. So we got 6 pounds, stretches, nope, not 4 inches, 6 inches. And our force is 3/16 sine omega t plus 3/8 cosine of omega t. And that's also in pounds. And we're going to try to find omega that leads to destruction. Okay. Let me share my whiteboard. So let's just start with the force that or the differential equation. So remember what that looks like. We have m, I'm going to go ahead and call it x if you guys don't mind. So mx double prime plus gamma times x prime plus gamma times x equals our forcing function. We were not told any kind of resistive force was happening, so we'll just go ahead and cross that guy out. We do know the force they told us was 3/16 sine of omega t plus 3/8 cosine of omega t. So that's what's going to go there, which means we have to find mass and K, M and K. So we know we've got a 6-pound weight. So let's use that first to find M. So M times 32 is going to equal 6. So M is 6 over 32 or 3/16. So that's just that's how you find what the mass is, and this is slugs. Now I will give imperial units this. That's an awesome name. That's an awesome name to have for your units of weight. The slug. I love it. And it totally makes sense, right? Like think about what mass is. It's your inertial quality. It's your resistance to motion. Well, if you're a slug, you don't want to move. I love it. It's perfect.
So sloths would have been cool too.
Yeah, I would definitely have taken sloth for that as well. And that's the only time you're going to hear me say anything about the imperial system is cool, because beyond that, it's all nonsense. Okay, so we got our M. So now let's go to the K. And again, remember what we know for Hooke's law is that F is equal to negative Kx. So we have a 6-pound force is moving at 6 inches. So I actually need to make that 1/2. Do you see why that needs to be a half instead of 6?
It's half of a foot.
Yeah, it's in feet because everything else is in feet, right? Like when we calculate the slugs, our gravity is in feet per second squared. So we need to do this in feet as well. So don't worry about the minus sign. We'll just F equals kx. So k is going to equal 12. All right, so if we piece that all together, this is going to give us 3/16 x double prime plus 12x equals 3/16 sine of omega t plus 3/8 cosine of omega t. So before we go any further, okay, before we even try to answer any of the parts of the question, because we haven't even answered anything in the question yet, are you guys okay with what we got going on here? Like, are you good with the setup of the differential equation?
Yes.
Yeah, we're feeling all right. Okay, so now what we need to do is see if we can find the frequency that's going to cause the problem. All right, so what kind of frequency do we need to get that blow up? How do we figure that out?
Well, I remember it was something like going to infinity, something like that.
Okay, so we're going to be going to infinity. And when we take a limit as we go to infinity, it's going to go infinite. But there's a relationship between the quantities that we have, the m and the k and all that, that leads to the blow up. Do you remember what it is? Well, let's just back up in turn, and not even with m's and k's and everything. Let's just think about the solutions to this guy. Like, forget about the non-homogeneous piece because that doesn't really matter right now, right? But let's think about the homogeneous piece. What has to be true to get the blow up? Well, I guess it does matter to this as well.
Well, I know the solution to the homogeneous is going to be complex roots.
Okay, so we're going to get complex roots. Let's actually find it real fast while we're here. I'm going to divide everything by 3/16 just to make life easier for us. I think that brings us here, right? If I divide by 3/16. So if we do the homogeneous piece real fast, r squared plus 64 equals 0. That's r equals plus or minus 8. So we know for the homogeneous, we're going to get C1 cosine of 8t plus C2 sine of 8t. Okay, so that would be the solution to the homogeneous. So cool, we got that. So let's think about what is going to lead to the huge blow up. Because if we go to particular now, say we're going to try to find y particulars. So we look at this. What is the guess going to be for our form?
It's going to be the same as our homogeneous, almost.
Right, since this is sine and cosine, this is going to be our guess. Yeah?
Yeah.
Okay. However, that might not actually be our, if this is our guess, then we're definitely not going to blow up. because whatever this form is, we'll get some sines and cosines plus some sines and cosines. It's just going to oscillate. But there is an omega that's potentially an issue. Like, what could I choose here for omega that would mean I have to use a different particular solution? Guess.
8.
Yeah, because if omega is 8, God forbid, right? Then we can't do a sine of omega t plus b cosine of omega t, because that's going to be exactly the homogeneous form. So what do we have to do? You'd have to multiply the sine and the cosine by t. And it's this stuff that's going to blow up. Because as time goes on, the sine and cosine just keeps bouncing back and forth, but the amplitude on that increases as we go further out. So the answer to the first part of this question, well, let's go double check what it says because I've forgotten it now. Oh, shoot. Hold on. There you go. Okay. So if we go back and look at this, it first says, for what value of omega will the displacement be unbounded? All right, so we got that answer. That's 8. If omega is equal to 8, this thing's going to blow out of control. All right, so then it says find the displacement if omega has this value. Assume that the motion starts from equilibrium with 0 initial velocity. Okay, so let's go back to this then. So that whole assume equilibrium with no initial velocity tells us x of 0 is 0, x prime of 0, 0, right? The first one's equilibrium. The second one is no velocity. And if we jump back down here and put in the 8s, we're solving this differential equation. So I would recommend that you guess the form over here, right? This particular form, and do undetermined coefficients. I think that'd probably be fastest. But obviously you don't have to do that. You can use reduction order or you can use variation of parameters, either way. But I think this will be a little bit faster. So is that far enough for you guys? You know where to go now, I hope. I forget who asked this one. But
So we're solving the bottom differential equation?
You're solving this differential equation.
Got it.
Which we've already partially solved, right? Because we already got the homogeneous. And you're going to add to that a particular form, but use this guess for your particular form. That makes it look like we're scratching things out, but use this form for your y particular. So use this guess. And then you'll eventually figure out what A and B have to be. All right, so is that good enough, Chev, for this one? But this also really illustrates why you need to do the homogeneous first, right? Finding the solution to the homogeneous is super important because it might affect what your guess is for the particular, and it can lead to a completely different kind of result, right? Like in this case, it's going to lead to blowing up as opposed to not if it was a different omega. All right, so we good with that one? It's okay if I switch over to number 6 from 6.2. All right, well, I'm not hearing any other questions, so we'll go ahead and jump over there. So we'll go back to the book. This one, though, we need to go find number 6. Oh, hey, look, imperial units again. All right, so this time we've got an 8-pound weight. Stretches a string 0.32 feet. Sure. The weight is initially displaced 6 inches above equilibrium. Okay, and then given an initial upward velocity of 4 feet per second. Find its displacement if the medium exerts a damping force of 1.5 pounds for every foot per second of velocity. I'm sure you guys just heard all of the dejection in my voice, my sigh. So number 7 from 6.3, yeah, we can, we'll go look at that as well, Jacob, after this. All right, so there's all the information from 6. Let's go put it together. Now, a couple things before I bounce over, just to remind you guys here. So when it says here the weight's initially displaced 6 inches from equilibrium, I'm going to go with 1/2 again, because I need this in feet. Everything else is already in feet. So that's the only thing, just to remember that that initial displacement is 1/2 of a foot instead of 6 inches. All right, so let me clear all this and we will start fresh. All right, so again, just like with the last one, we want to go with mx double prime plus gamma x prime plus kx equals f of t. Now, we were also, though, given some initial conditions. So I want to write those as well while we're here. So it said that it was displaced upward by 6 inches. So that's going to be 1/2. But my initial condition is actually going to be x naught equals minus 1/2 foot. Are you guys okay with the minus?
I thought that if it was below equilibrium, it was minus, not above.
Okay. The way that we set this up was, remember, we had gravity going this direction as this was positive. I don't know if you remember that, but when we set this all up, we had down being positive. So if our displacement is upward, it's actually going to be a negative 1/2 foot. No, kind of, maybe not.
I'll roll with it.
Okay, well, we set up everything so that downward was positive. So then x naught, since we were sending it upward, that's going to make that also negative, but in this case, negative 4 feet per second. So, and you can actually use this to help see why it has to be this way. Just look at the force bit, k times x. So if we displace upward, we need to have positive force, right, going down. And since Hooke's law is negative kx, upward has to turn positive. That's what I use to help me remember what's going on here. Or the fact that I've done a billion of these, and so I know that down is positive. So those are going to be our initial conditions then. We also, though, have that f of t is equal to 0. There is no forcing function. So that means we got to find m, gamma, and k. All right, well, let's go get them. So I'll start with the m. We know that the force was 8 pounds. So that's going to be m times 32. So m is 1/4. From the Hooke's law bit, we know that that force of 8 pounds made it displace 0.32. So k is going to be 8 divided by 0.32, which I think is 25. And then lastly, we go to the gamma. Force is equal to gamma times v. And we were told it was 1.5 pounds for every 1 foot per second. So gamma is going to equal 3/2. So we'll go ahead and put all that stuff in, and we now have 1/4 x double prime plus 3/2 x prime plus 25x equals 0. And I'm going to go ahead and multiply by 4 just to get rid of the fractions, mostly because I can. And we're here. All right, so before we move on, are we good with that differential equation? Any questions on it? Okay, so now we get to solve this differential equation. And I really feel like I don't need to go any further, right? You know what you need to do?
Yeah, that's good.
Yeah, since it's just homogeneous, I'll do one more step for you. Solve that, find your r's, depending on what the r's are, put it into the right form, and then you're good, because there's no particular solution. We don't have to worry about that. And then you can use your initial conditions to find your C1 or your C2. All right, so there you go. So I know it's cumbersome when you've got these imperial units, but if you just remember, pounds are force, and make sure everything's in feet. It's the same old, same old. It's just the units feel weird. Okay, so let's go look at that last one that Jacob asked for from 6.3. And I forget, which number was that again, Jacob?
It was number 7.
Number 7, okay. So this one says, find the steady state current in the circuit described by this equation. Now, we haven't talked about, I didn't mention steady state. Hopefully you kind of caught that as you were looking at the book. But steady state just means limit as t goes to infinity. What's this thing going to look like as t goes to infinity? Because it's going to settle down. That's your steady state. So let me just write this down real quick. All right, and we'll go back to the whiteboard and see what we can do. All right, so I'm going to clear this. So for this one, we had 1/20 q double prime plus 2q prime plus 100q equals 10 cosine of 25t minus 5 sine of 25t. So first thing I would do is actually multiply by 20. I really don't like fractions. All right, so let's just think about what we have to do here. Start with the homogeneous. So r squared plus 40r plus 2000 equals 0. Yeah, we'll go ahead and go all the way and get this. It is going to be complex. That's minus 6400. Is that right? Yeah, minus 6400. So r is equal to minus 40 plus or minus 80 I divided by 2, which is negative 20 plus or minus 40i, I think. So that makes our homogeneous C1, or hold on. Let's do the exponential piece first. E to the minus 20t times C1 cosine of 40t plus C2 sine of 40t. So there's our homogeneous. So then we got to get our particular. And for this one, I'm going to make a guess again. I'm going to make the guess that it's A cosine of 25t plus B sine of 25t. And I'll leave this to you to figure out what the A and the B are. But I think undetermined coefficient is going to be fast enough here, especially since we have a different function than what we found when we solved the homogeneous. So that's going to get you your Y. Now, I know that I didn't actually calculate those for you, but let's just think about what this is going to look like. So your A's and B's are going to be the right 10 minus 4, what, like, who knows? And then you're going to get plus the e to the minus 20t C1 cosine. All right. So again, you'll have numbers for A and B, but that's what our answer looks like. So to find C1 and C2, you would need to know some initial conditions. But if you look at this problem, it doesn't tell you anything about the initial conditions, right? It just tells you find the steady state for the current. Let me actually, this is Q equals, not Y equals. All right, so here's the question. What happens to this as t goes to infinity? Well, if we start with this homogeneous piece, you're going to see that that goes to 0, regardless of what C1 and C2 are. This negative exponential is going to drive that down to 0. These two, well, they're still going to do what they do. I'm not actually going to evaluate it for t because it's going to oscillate. But as t goes further and further out, this is what our charge is going to look like. it's going to oscillate whatever that particular solution is. So this would be our steady state in the charge. But I think if I remember in the question, it said find the steady state in the current. So how do we get current from charge? How are they related? How are Q and I related?
Q equals IR. Right?
So V equals IR is the voltage of a resistor.
Q equals I times T, right?
Okay, so not necessarily I times T. That's if it's constant.
Just take the derivative.
Yeah, so I is dq dt. So Jacob, when you said take I times T, that would be, again, if it's constant Q. That's what that would end up being. But all right, so if you want to know the current, you just differentiate this thing. So it's going to be minus 25A sine of 25t plus 25b cosine of 25t. So whatever the A and the B you found through your undetermined coefficients, put those there. And that will tell you what the current is going to look like long term. Right? In the short term, you get the effects of this, but that eventually is going to go away. So is that a good enough push for that one? Who was that? Jacob, I think, asked about that.
Yeah, that's perfect. Thanks.
Okay, cool. You're welcome.
So, I'm just thinking about like the answer to this question and just trying to picture it. So the current's gonna increase, decrease, and go to zero at times, and then other times it's, it's just gonna keep repeating, right?
Yeah. So this current, it's going to be an alternating current, right? I mean, let's just be real, right? We've got AC and we've got DC. This is going to be AC. You're going to have an alternating current because you can combine those two, right? Using some trig into a single sine or cosine. And so your current is just going to be oscillating. It's going to be alternating from, a positive to a negative flow. Again, depending on what the A and B are, will give you what the amplitude of that is. But yeah, it's just alternating current. So this circuit, long term, is going to have alternating current. But we're supplying it with alternating current. That's what this is right here, right? That's alternating current. And that should make sense, right? If we had this circuit and we plugged it into wall socket, we should expect that what's going to happen in that circuit will be alternating. We'll have alternating current because we're driving it with an alternating current. So I don't know if that helped answer your question or anything, Bradley, but
No, it did, but it also brought me to another question.
sure.
Is E and M quantized?
Oh, that's a very good question, right? Because when we're in modern physics, when we're talking about quantized energy, we just talk about like photons that are being released and all that. So, yeah, it's a good question. I don't think I'm going to answer that just yet. I want you to think about it.
Well, I'm already thinking about it, but okay.
I really what it gets at Bradley is you got to think about what's actually creating the energy in E&M. What's actually the mechanism that causes there to be electromagnetic energy? And I think we're actually going to talk about that tomorrow. If not tomorrow, it's coming up soon. when we talk about like harmonic oscillators and things like that. So just so you know, you're just a slight step ahead of where we're going to be in, or where we are in modern physics. I love it though. I love the fact you're starting to think that way. That's huge. Huge. All right. So any other questions from DiffEQs? We'll save modern physics questions for modern physics class.
You know they're one and the same.
Yeah, there's a lot of parallel between them. That's absolutely true. I mean, actually, everything. Well, so the joke in my house forever when the boys were young and they would ask me questions. You know how kids are, right? It's like, hey, Daddy, why is the sky blue or whatever? I would always just without a beat go, physics. That was always my answer, just to anything. It's like physics. And then my wife and I used to get into little arguments about. She's like, "Well, no, not everything is physics. Like, what about life science stuff?" And I would always break it down to, "Nah, it's physics, right? You want to talk about dreams? Well, how do dreams happen? Well, it's because of all the, the firing of the neurons up in here, which are just electromagnetic energy. So physics. Anyway, so my answer to everything is physics. So that's why when you say, well, they're one and the same, I'm like, yeah, everything's physics. Although math is its own thing. However, math is integral in being able to do physics. So then maybe everything's math.
It's both still.
Yeah, I'm all good with that. I mean, you think about like where did a lot of math come from? Well, it came from observing the physical world and trying to describe it. I mean, that's the only reason we have calculus. But
Sort of a chicken and an egg situation a little bit.
Yeah, totally. And I am convinced that mathematics was created by humans. I know there are a lot of people that don't like that. I really don't like that statement, but I do. I think math was created by humans. There's a human perspective to mathematics. I am convinced that if some other entity created their own version of math, be it aliens or dolphins or whatever, that it's not going to be the same. I mean, it's going to be based on logic and everything, but it's going to be slightly different because of the perspective of the, of the creature, of the entity. But math was invented to explain what we see out there, even as simple as, well, how many velociraptors are coming to attack us. Yes, I know humans and velociraptors weren't around at the same time, but it sounds more fun. But even something as simple as that, well, I'm trying to describe how many things are going to come and try to eat my tribe. Well, I need to have something to describe it other than lots. Well, how many lots? Big lots or small lots? Right? So yeah, they kind of are one and the same. So then Ross just put there for chicken and the egg. The chicken comes first since the egg requires protein, which needs a body to begin with. Well, but where did that body come from?
See, I think the answer to the question is it's the chicken nor the egg didn't come first. It was the previously evolved thing before a chicken.
The thing that worked itself into a chicken?
Exactly. So it's neither.
But then that thing was birthed from an egg, so then that thing's egg came first. So
but was it birthed from an egg?
All right, fine. The bacteria came first. How about that?
there we go.
The amino acids and the nucleotides and all those actually came first. But see, this is the problem talking philosophy with math and science people is we destroy everything, right? Again, with the tree falling in the woods. Does it make a sound? Well, it obviously creates some sort of a pressure wave. So yes. Oh, but sound is perceived. No, sound is a pressure wave.
Yeah.
Yeah, but anyway. Yes, the chicken or the egg. I definitely kind of fall into, well, because if it doesn't say specifically a chicken egg, then the answer is definitely egg, because there have been eggs long before there have been chickens. This we are quite certain of. But Yeah. Anyway, enough about eggs and chickens. Anyway, go ahead, Bradley. You were about to say something.
I'm curious. It's like, you know how you say, math is human invented, which I have to agree with you. It is, But I'm curious if like fundamental constants would be the same amongst, other intelligent life, like Fibonacci sequence or E, that sort of thing.
That's a good question. I think pi. I think the idea of pi would definitely be known because circles are so common, and pi is just the ratio of the circumference to the diameter. And so you got to think that any evolved creature that's going to be studying circles or geometry whatsoever, or be interested in that, is going to see that shape and know those two measurements and probably see that there's a constant ratio there. So I think pi for sure. I would love to say that E would be known, but that kind of requires a lot of what we did to sort of be naturally what you want to do, like differentiation. I don't know that differentiation would matter to someone who's not human, or integration. But if they know derivatives and integrals, then I guarantee you they know about E. Just because of the fact that e to the x is the function whose derivative and integral are the same, that would be something you would figure out. But I don't know that that's quite as natural of a thing in the world as a circle. So E, I don't know. I really don't know, because that's the total just mathematician. Yeah, what the hell? Let's do it. Which that could be just a humanness thing.
But then it works though.
Oh yeah, no, it definitely works. And then some of the other physical constants, like the gravitational constant. See, there you get into the units thing, right? Like when we talk about the speed of light, 3 times 10 to the 8th meters per second, they would probably, other entities would come with different units, but they would still know about C.
Aren't all the metric units given like a sort of universal equivalent? That way we can communicate them easily to any alien intelligences that we encounter. Like the meter is equal to this distance light travels in such and such time or something.
Yeah, but like if you go, okay, so a meter is the distance light travels in a certain amount of time, they'd have to understand our time scale.
That's true.
Right. And so, yes, they have changed all of the metric units to be based on physical constants. Right. So it's no longer a kilogram is this mass that's in some, museum in France or whatever, which is what it once was. A kilogram, there was the official kilogram. It was the like chunk of metal that was 1 kilogram of mass. But we no longer have that. They're all based on physical constants. But that would require even, some other group to be able to understand our units of measurement. So, but I think any other scientifically intelligent group would understand the nature of the maximum speed. I think speed of light would be known. Gravitational constant, probably. I think that probably would be one. But then when you start getting into other things, I'm not certain. Like anything to do with temperature, absolute zero on whatever their scale would probably be known.
What about the Planck temperature, the opposite of absolute zero?
The temperature where everything breaks down,
Yeah.
maybe.
I guess that assumes that our models are accurate, though.
Yeah, and that's true too. Like our definition of things breaking down or whatever. And then you think about other constants like Boltzmann's constant and Avogadro's number, and things like that. There's a decent chance for Avogadro's number. I think that there's a decent chance that would happen. Again, it might be a different number, like, because they'd have a different number system than ours probably. But I don't know. That kind of stuff is fun to think about for sure. And I know that non-mathy science people really don't like the idea that math wouldn't be the universal language, but I'm not convinced that it is. Like our infatuation with primes. I don't know that other entities would give a shit about primes. So when we start telling them, hey, 2, 3, 5, 7, 11, they're like, what? You're just giving me random numbers. What the hell?
What are numbers? Like,
Yeah.
we don't even know that other intelligences would conceptualize numbers the same way we do.
Right. So. Oh, look at that. Even math class turns into philosophy. I love it.
So everything's based on philosophy and not math or physics, I guess.
Everything's based on perception. Everything's based on perception.
Which bums me out because we're flawed.
That's the understatement of the year. But yeah, I mean, so is there any absolute? I mean,
yes.
This is the kind of stuff that keeps me up at night. Is all right? Well, so I tell you that this is purple, and we can all agree that this is purple. But are you seeing the same thing that I'm seeing?
I think about that all the time.
Right, and maybe not. I mean, we all agree that when you see that, it's purple, but your purple and my purple, and what actually strongly suggests that we don't perceive things properly is think about your voice. Think about the voice that you hear when you talk versus the sound other people hear when you talk. Right now, I have a ton of experience with this because everything I do gets recorded. And so I end up hearing my voice externally and it sounds completely different, right? We all agree it's my voice, but it sounds completely different. We perceive it differently. And if that's the case with just the sound that our voice makes, how can I trust any of my senses that what I'm seeing, what I'm hearing, what I'm tasting, what I'm smelling, like any of it, how can I be convinced that, well, Jordan tastes the same taste as I do, right? When he bites into a Frito, is he tasting the same thing I am? Right? Or when I smell, fresh cut grass, Jesus smells it too, and he knows it's fresh cut grass, but are we smelling the same thing? Does it smell the same to both of us? And like, that's trippy. That's entirely trippy that I'm convinced that they're all different because we're all going to experience the world slightly differently. And yet we can all come to a consensus of, oh yeah, I smell the fresh cut grass. Oh yeah, I taste that saltiness of the chips. And, I think that's pretty amazing. And then you throw onto that the fact that humanity has hundreds of different languages, and yet we can still all agree that this is red. Like, it trips me out. But
yeah, I think almost like a certain degree of like almost faith is required when it comes to like research and science, when it comes to like, yeah, there are objective truths that we can measure and like say, yes, this is that, but like, we can never really get any sort of confirmation that that's actually the case.
right. And there does have to be just a little bit of a level of, yep, your perception of this thing, whatever, even though it might be different than mine, we can still agree that this is what it is. So, but what the hell, it doesn't even matter. We just all live in the matrix anyway. So, we were just put into a simulation where we would end up having this conversation. So it's all moot.
The thing that trips me out is thinking about evolution. that sometimes makes my skin crawl a little bit.
In what way?
Well, just thinking about the theory of evolution, and it seems reasonable and completely logical. And then I look at my kid, and he looks like a monkey, and so do I sometimes. And it kind of makes my skin crawl a little bit.
If you want that sort of feeling concentrated, look at like embryo development and stuff like that. That stuff is insane. Like the way it replicates ancestry, it feels completely surreal, you know.
Yeah, or you look at, like you're talking about embryos, look at a human embryo and compare it to embryos of other creatures, and at certain stages you wouldn't know the difference, right? At certain stages of development you wouldn't know that that thing's a human versus an alligator. Yeah, that's kind of trippy for sure. Face it, the universe is awesome. There's all kinds of cool stuff, and the fact that the questions will never all be answered, I mean, that's good and bad, right? It's a bummer because of course I want to know all the answers, but there are always new answers. There's always something to look forward to, right? So there's always something to learn, always something to find out. And I don't know about you, but I think that's pretty cool. So speaking of learning things and finding stuff out, but a good job, by the way, of derailing me for, well, looks like about an hour now. Let me actually show you Euler equations. I want to show you just a little bit of something new here. But specifically, these are a type of equation. Let me just clear all this nonsense from before. These are a kind of equation that have singular points that are a problem when x equals 0. Things don't, quite work out the way that we want them to. But they are still kind of useful. All right. So let me go ahead and show you these real fast. All right. So an Euler equation has this form. So, oops, hold on a second. My pen's not working. All right, hold on a second here. Let me stop sharing. Try this again. There we go. All right. Hey, look at that. It works now. Okay. So, oh my God. My computer is having trouble. So I have no idea where I am on the screen, by the way. I can't move my windows and I just have like a chunk of whiteboard. So we'll see how this goes. So an Euler equation. This is one that comes in a very specific form, but it's actually kind of nice, and it looks like this. We've got, well, x squared. God, I think you guys have me all thinking about other things now. Thanks a lot. Okay, so it's gonna be a times, yeah, I did want x squared times y double prime plus b times x times y prime plus c times y equals 0. Okay, so this is at least a homogeneous Euler equation. They can also be non-homogeneous, but we're going to talk about the homogeneous first, just how we get the solutions.
Can they be higher order?
They can be. Usually we reserve Euler for just the ones that are second order, but you can continue the pattern. So like if we have a y triple prime, that's going to be times an x cubed and so on down the line. Okay, now the first thing I want you to notice is that this definitely does have a singular point, right? If I were to rewrite this so that it's just y double prime, I'll leave the a, but let me divide by x squared. right? This is the same form here. And so that we see that x equals 0 is a singular point. So singular points, as we've seen, are potential problem spots that we kind of want to avoid. Now, you think about trying to do this with a power series. That's totally fine. It's going to completely work. We just have to make sure we're not centered at 0. But that's going to make this pretty rough. I don't know if you remember when we did one on, might have been, I think it was Friday, when we had something like this centered and we had to center it at like 1, and then we had an x that we had to pass through. And you remember how we had to like break it up into 2 different sums, and then it like, I mean, it got gnarly. This is going to be pretty rough if we're not centered at 0. But if you look at this equation, you can kind of see why maybe this isn't quite so bad. And in fact, we could even make a guess. I want you to think about, forget about this one where I divided out, where we got the singular point. Okay, but just go back to the original. Think about what we need for our function. Our function has to be such that when we differentiate it and multiply by x, we get something similar. Then when we differentiate it twice and multiply by x squared, we also get something similar to what we started with. Can you think of a function that does that?
E or sines and cosines.
Okay, so the e's and sines and cosines actually are going to be a big problem here. Because if you differentiate an e to the x, let's say, you get another e to the x, e to the x. Now we've got e to the x and an x e to the x and an x squared e to the x. And those things aren't going to cancel out to get a 0. And
E to the power of x with the power on it?
Okay. Yeah, a similar problem with sine and cosine, right? But as Jacob just said, well, what if we have x to a power? Right? Like let's say it was x cubed. You differentiate, we get 3x squared times x. Oh, that's more x cubes. 3x squared differentiated twice gets us 6x times x squared gives us more x cubes. So for this one, it's really reasonable to suggest a guess of y equals x to the r. Because as we differentiate, we're going to decrease that exponent by 1, which means every time we multiply by one of these powers of x, it's going to give us the same thing. So this is completely analogous to when we did them originally with just constant coefficients, right? When we just the a, y double prime, by prime, and cy, and we went, hey, let's guess exponential. It's the same kind of argument. It's the, let's try x to the r. So if we do that, let's just kind of see what happens here. The derivative, of course, is going to be r times x to the r minus 1. And the second derivative is going to be r times r minus 1 times x to the r minus 2. So if we put that back in here, we're going to get ar times r minus 1 x to the r plus br times x to the r plus c times x to the r equals 0. We can factor out the x to the r. And we get ar squared minus ar plus br plus c as our factor. And so I want you to see what this leaves for possibilities. I mean, one is, of course, if x to the r equals 0. But that's going to be only true if x equals 0. And we want to look for solutions that work everywhere for all different x's. So that leaves us here, where we've got ar squared minus ar plus br plus c has to equal 0. Well, just like before, that gives us a polynomial that we need to solve. So we are going to find solutions to this, and those roots are going to be our powers on x. And those are going to give us the solutions to the Euler equation. So it's kind of a neat little trick, using kind of the same trick we've used before. But just like before, there are going to be three cases. We're going to get where we get, the first is that we get two unique r's. The second is where we get one r value. I'm going to put here repeated, right? Because it could be that this polynomial gives us just the same r twice. And then the third possibility is going to be complex r values. So let's look at each of those three different scenarios and see if we can figure out what the solutions are and what we get. Okay, but again, it's all going to come down to this polynomial right here, which is going to be determined by our original differential equation. Okay, so let me erase all of this stuff. And let me give you a specific example. Okay, so let's see if we can find the solution to this Euler equation. All right, so where's my draw? There's my draw. Sorry, everything here is all tangled up on me. All right, so let's try this one. Let's go with x squared y double prime plus 5xy prime plus 4y equals 0. And we won't worry with an initial condition right now, but we know what we're going to have to do when we get there. All right, so first things first, let's create our polynomial. So a is 1. So we're going to have r squared plus b minus a. So 5 minus 1 is 4. And then we have plus c. Whoops, that's supposed to be an r. Sorry about that. Plus 4 equals 0. All right, so we can factor this. It's r plus 2 times r plus 2. So we get r equals minus 2. All right, so this is the second case where we have one r value repeated. Now, in this situation, you already know what one of the solutions is going to be. We're going to create our fundamental set. One of them is going to be x to the minus 2. Right? We made the guess of the form x to the r. So in this case, we get r to the minus 2. So we're going to have x to the minus 2 as one of our two solutions. Okay. So then the question is, what about the other one? Now, if it had been two unique r values, I think I don't really need to show you an example of that, right? But suppose we had factored and we had gotten two unique r values, our solution would have been y equals c1 x to the r1 plus c2 x to the r2, right? Super easy. But we don't have an r2. So what did we do before? What did we do before to take care of repeated root?
Didn't we multiply by another function?
Okay, we did. We multiplied by another function. And what we ended up finding when we did the exponential pieces is that extra function was x. Well, clearly we can't just multiply by x. I say that with confidence, clearly. Do you see why that's not an option?
Because we're gonna have a degree less, or I guess higher than what we have, and that might ruin our homogeneous nature.
Yeah, okay, so think about that. We do this x times x to the minus 2. That would give us x to the minus 1. But if that were a solution, it would have shown up. It would have shown up through this process. So that means we're going to have to end up multiplying by something other than x. Okay, this y2, it is going to be x to the minus 2, but times something. So we're going to do the exact same trick you've done a bajillion times, which is multiply by an integrating factor. See what that integrating factor needs to be. So let's do that with this guy. Let's see if we can figure out in this repeated root scenario what the other function is going to be. All right, so let's make our guess. We're going to guess y equals mu times x to the r. Okay, so y prime is going to be mu prime times x to the r plus r x to the r minus 1 times mu. And then y double prime is going to be mu double prime times x to the r plus 2r x to the r minus 1 times mu prime plus r times r minus 1 times x to the r minus 2 times mu. And this piece came from the two portions from the product rules in there. All right, so now we're going to put this in here and see what we get. So I multiply by ax squared, and I'm going to combine, again, like we always do, the different derivatives of mu. So I'm going to get mu double prime times ax to the r plus 2. Mu prime is going to get this times ax squared, so 2ra x to the r plus 1. And then this one's going to get times bx, so plus b x to the r plus 1. And then if we go to the mu's, I'm going to get r times r minus 1 times a x to the r plus this one times bx gives me br x to the r. And then the last one's going to give me c x to the r. And that's all times mu. All right, well, just like before, just like every other time, see this pit right here? This is going to equal 0. Because this is the polynomial that gave us the r that was our solution. So that all goes away. So that means we reduced our order just like every other time. Hold on, since those are both r to the 1s, let me just combine them real quick here. So 2ra plus b times x to the r plus 1. And this, my friends, is separable. So if we rename those mu primes again to something else like w, W is equal to mu prime. So we just know we have to integrate what we get from this to get our mu. And I rewrite this. I get W prime over W is equal to 2RA plus B over A negative times x to the minus 1. Cool. So integrate those things. All right, well, this is going to give us natural log of W equals minus 2RA plus B over A times the natural log of X All right, so we're here. Now, before I go any further, I want to simplify this a little bit. Because we know that the R is not random. The R is such that we got a repeated root when we do this process right here. So let me just erase a little bit here. We'll come back to this equation in a second, but let's do this to finish off. And I did not mean to erase that. Let me rewrite that. So we had W was equal to U prime. All right. Now go back to what the polynomial was. Right? Because we started with the A times R minus 1 plus B times R plus C. That was R equal to 0. So it looked like that. But now let's think about what we need for a repeated root. For a repeated root, we need this to equal 0. Right? That's the, this is what's inside the quadratic formula square root. So that has to equal 0 for that to happen. Okay, well, if this equals 0, I'm just going to tell you, do a little bit of work on this. And if that is true, think about that repeated root. That repeated root then is going to be R equals negative B minus A over 2A. Because we get the plus 0 business there. So negative 2RA is equal to B minus A. So take this and replace it for the negative, or for the 2RA, I should say. So what this ends up doing for us, this is pretty nifty, is we get the natural log of W equals negative natural log of X. So hopefully you can see that, because there's a negative B here, cancel with this positive B, negative A over negative A is negative 1. But regardless, that gives us W equals X to the minus 1. All right, well, mu, remember mu prime was equal to W. So mu is the natural log of x. All right, so very long story short, when we get a repeated root, y1 is going to be x to the r, and y2 is going to be x to the r times the natural log of x, that guy right there. So it's exactly the same idea, exactly the same idea. It's just we get a different multiplier because this has a different form. So if we go back to the one that we were working on just a little bit ago, remember what we had found?
That's
Yep,
the statement every time for repeated root.
for Euler equations. Yep.
Cool.
So y1 was x to the minus 2. That makes y2 x to the minus 2 times the natural log of x. So our solution to that differential equation then looks like this. Huh. Okay, cool. It's just we use a different form because it's a different kind of differential equation. But notice that we were actually able to get the solution at a singular point without having to worry about power series. And that's huge, right? We would much rather have the actual function, not some power series that then we have to convert back to the function. No, here it is. Here is the solution. Okay, but this is for Euler.
I mean, doesn't the power series still kind of show itself because it's x to the r?
I mean, kind of, but it's not a power series now.
Yeah.
It's just one exponential piece as opposed to the sum of all of the exponential pieces.
I'm curious if you did run the power series on this, if you would get something similar to that.
You would. No, you would get exactly this. You would. It would end up giving you like a sum that becomes the natural log. And then there would be like the extra piece that you're adding onto it, which would end up being that x to the minus 2. So yeah, no, it definitely will work. But why? Why bother if we don't have to, right? And I think we can all agree on that. Power series are cool and fun and awesome. Maybe not fun. But if we've got faster, easier ways, let's be mathematicians. Let's take the faster, easier route. All right, so that's what we do when we've got repeated roots, which now leads to the question, well, what do you do when you have complex roots? Well, I'm sure it's going to come as no surprise that this is going to lead to some sort of a sine cosine business, right? That should be like terribly obvious with how everything has worked out so far. So let's actually see what it does and how it behaves. Okay, so let's go to this set where we have complex roots. And so we'll do the same thing as we did before, where we're going to have r equals lambda plus or minus omega I. At least I think that's what the letters we used were. So if we kind of follow the same process, we're going to get y is equal to x to the lambda plus omega I, y1. So this is going to be x to the lambda times x to the omega I. Now, what we're going to do is we're going to change this to base e. And we're going to do that by making x e to the natural log of x raised to the omega I. Right? How many times have we done that trick? So this gives us x to the lambda times e to the omega lambda x times I. All right, well, we already know what we do when we have e to some power of I. That's what gives us our sines and cosines. So we're going to get cosine of, let me make this a bracket. Omega natural log of x t, or sorry, no t, just omega natural log of x plus c2 sine of omega natural log of x. So notice that that looks like almost identical, except now instead of t or x, there's a natural log of x. Just like when we multiplied, instead of multiplying by an x, we multiplied by a natural log of x. All right, so now you're good to go for any Euler equation. Two unique roots, c1 x to the r1 plus c2 x to the r2. Repeated root, x to the r and then x to the r log x. Complex roots, x to the lambda times c1 cosine of, now it's omega natural log x, and c2 sine of omega natural log x. So I'm going to show you an example of complex roots real quick, but you'll see that it's not really that big of a deal as long as we remember this form over here. All right, so let's look at this example. Let's say we had x squared y double prime plus xy prime plus y equals 0. So we're going to make our polynomial. It's ar squared, so 1r squared, plus b minus a r, so 1 minus 1 times r, plus c. So this becomes r squared plus 1 equals 0, which gives us r equals plus or minus I. All right, so this is complex where lambda is 0 and omega is equal to 1. So here's what our solution is going to look like. We get x to the 0, that's just 1. Then we're going to get c1 cosine of 1 times natural log of x, and then c2 sine of 1 times natural log of x. And there are your solutions. So pretty neat, actually, pretty neat little form that leads to some pretty simple solutions. But check this out. Think about the fact that we had a singular point at 0, and that was a problem. Notice that 0 is still a problem in our solution. I still can't be at x equals 0 because the natural log of 0 is undefined. But as soon as I'm off of 0, this thing is perfectly fine and reasonable and everything's great. So even in the process of finding our solutions still make us avoid x equals 0. All of them do, right? Think about just the repeated root, x to the minus r times, or x to the r times natural log of x. Okay, again, natural log of x can't equal 0. And then the other ones, we have to avoid it whenever r is negative, which happens quite frequently with these things. So the fact that 0 is a problem gets preserved. It's not like it just goes away. It's just we have a nice, easy way to finding the solutions otherwise.
I'm curious as to what sort of things out there in the world would have positions like this.
That would give you, or that would lead to Euler equation differential equations.
Yeah.
Yeah, that's a good question. I don't know any off the top of my head. So they definitely are not ones that I've seen in my experience. But to be honest, most of the differential equations I've seen in real life are either kind of like the spring ones that come from just simple mass times acceleration kind of things, or they're partial differential equations, which are a whole nother beast in their own right. So, but I don't know. I'll look into it. I'll see if I can find some real life scenarios that lead to Euler equations. I just don't know any off the top of my head. All right, well, I think this is a good place to stop. So on Wednesday, we'll probably just talk a little bit more about Euler equations, kind of wrap up that discussion. And then we'll just sort of move on and go on to another technique for solving differential equations that applies to any kind of differential equation. And it uses this thing called the Laplace transform. So on Wednesday, I will introduce you to that. All right. So with that, I'm going to go ahead and stop our recording.